Hello, everyone. My name is David Leclerc. I'm the host of the ChUG podcast. We're here today to talk about Spectral flow time tree platforms available in the market. And we have Ryan Duggan, which is the principal now at AbbVie.
Hello.
Ryan. Dave Adams runs the core facility at the University of Michigan. Hello, Dave. And Rachael Sheridan is at Van Handel, not Helsling, as I keep messing it up. The vampire hunter technology. It's like very serious research done over there. Hello, Rachael.
Hello.
And Rachael is in part the reason we're having this discussion today, because we were sitting, both of us were sitting at the Sony booth at the last GlyphCon meeting, and we started arguing over the claims made by Cyto to sell their platform. There's a lot of head scratching over there, lots of things that basically fights or go against the basic training we've been provided to our users over years. And I think it's a bunch of stuff that we need to revisit, make sure we got it right. Maybe Sony is up to something. Maybe we need to upgrade our knowledge.
And so I need a refresher on physics and electronics, please.
Exactly. So what I propose to do, guys, is we'll just do a quick review of the available platforms on the market, and then go into using the claims done by Sony. We'll kind of revisit our knowledge of flow time tree and spectral flow, and how it all ties up together and everything. So that should be awesome, right?
Sounds good.
All right. In the spirit of bringing these platforms by tiers, I decided to bring them by number of detectors. So we have Bill Eads call them the branch and tree instruments. So BD A5 SE and the Bigfoot. You guys have, I have an Aurora. I know these platforms through reading material, but have you guys played with these instruments? I have a Bigfoot, actually. What am I saying?
Yeah, I have a Bigfoot, a couple of Auroras, an S8, and an ID 7000.
Right. Have you played with the A5 SE at all?
No.
No. Rachael and Ryan?
I have the most experience with the Aurora platform.
Right.
I have seen a bit of the ID 7000 and the A5 SE, and I have been putting off upgrading my S6 to Spectral for 2 years.
Okay.
But one of these days I will probably do it.
The S6 will be another branch and tree type platform.
Yes.
Right?
Yes.
Right.
If you're going to call the A5, you have to put the S6 in the same bucket.
Right.
Yeah. Can you actually just describe what branch and tree means and why it would be different than something else?
Right. So my take on it is essentially branch and tree is like a traditional instrument, but you decided to fill out all the gaps by adding more detectors and more filters. And so in the end, you end up with a platform that's kind of a hybrid between traditional and spectral, in that it allows you to look at the entire visible spectrum with most of the markers without providing you the how would you call it, the power to separate the really closely emitting fluorophores, right?
So I'd say like the branch and tree has more to do with how they're doing it, so that they're going to use the combination of the dichroics and the band passes, and it's one wavelength at a time. Everything else goes to the next bucket, or they split it up. But then some of these other systems, like the Sony's using dispersion optics, it's got is it a diffraction grating or a prism in there? And uses a multi-channel PMT, so it does less bouncing around. It's kind of how they're isolating wavelengths.
Sony used to be a prism, but now it's different. It's different technology.
Diffraction grating now.
Mm-hmm.
Yeah.
Mm-hmm.
Maybe I'm wrong, but I get the feeling when you have a branch and tree, you were planning to do a traditional flow instrument that had tons of detectors, and then you realize, oh no, I need to switch gear and make this a spectral, and without having like, instead of like changing your entire optical system, you just add a bunch of. So it's kind of an exit route to prevent you from having to redo your whole project.
Yeah, and I
Yeah,
guess
Yeah.
go ahead,
it's a
Dave.
traditional optical bench, just with a lot of detectors. And I would argue that, the point about seeing the whole visible spectrum, it's not necessarily complete, but it's good.
Mhm.
Is there, so that's another thing that gets argued. When is it full spectral? What sort of spectrum coverage do you have to have? Or is it
Yes.
just if you use the math, the unmixing math rather than compensation?
Sony really wants us to have this debate, and
I
they
know.
want to cut the line and says, okay, you branch and tree people, you're out of the game. It's us and SciTech now.
Yeah, so I mean, I think people think spectral's about the math more than, necessarily the completeness of the optical bench, but there is a lot to be said for, complete optical benches.
Sure, because I've run spectral unmixing on my 12 parameter Fortessa data. And it's, maybe a little bit better in terms of kind of the shape of the negative population for the most part, which gives at least a perceived increase in resolution. But yeah, I guess kind of that whole definition, any instrument could have a spectral unmixing algorithm applied to it, but it's not like we're going to call those spectral analyzers.
Right.
And I think there's probably some baseline, amount of the spectra that you're covering, and maybe even the resolution at which you are interpolating all of the different bands of light coming from your samples that might have to fit into a definition of a spectral analyzer. But
Yeah.
I don't know that, a branch and tree configuration necessarily excludes you from calling yourself a spectral cytometer.
I don't think so. I think so. I had high hopes at some point back in the days where I could use some mixing algorithm to just separate, say, GFP and YFP on my Fortessas, like 4 lasers, 15 detectors, and the data is just not very good. Like you're much better off using proper filters, and so in that sense, yeah, there's a limitation to calling a 15 detector instrument spectral. But I think when you reach like 50 detectors, okay, you're part of the gang. Come on, it's second type of instruments, your the BDS8, basically mid-range number of detectors in the grand scheme of thing. When you compare it to like branch and tree would be the low end of our number of detectors, Sony would be the other one. These guys are right in the middle. Aurora has taken the market by storm, and that's what most core facility will have. And it seems with the 60-something detector set, we reach what's the highest number of markers we've published so far? I think it's at 42 or something.
Saw some posters with 50 at Cyto.
Right. So we're reaching quite decent level of complexity here. Anything special that needs to be said about the technology behind the Aurora DS8? The way the way that the signals are broken down with branch and tree. Sony has this Rachel, how do you call it?
The
Dispersion.
Sony,
Dispersion.
yeah, it has some dispersive optics. That's the diffraction grading and multi-channel PMTs.
Right. And so
Yeah.
Aurora use APDs, and how do they break the signals again? I remember a figure of a.
It's been a while since I looked. I seem to remember like a mirror and then a
Right.
bandpass filter in front of each APD.
Right.
So, which reminds me more of a Cytoflex style.
Yeah. So each detector has a small bandpass filter. Put them together, you cover 420 to 800 something nanometers.
Mhm. And I don't know the S8 APD layout for the optics. Dave, what's it look like in there?
Similar to the Aurora.
Okay, nice.
And really, it's these bandpass filters that are, the magic, because, on your branch and tree, you've got traditional bandpass filters, which are really optimized for particular dyes, but aren't necessarily good in for spectral layouts. So you've got some, you're cutting spectra with branch and tree in odd ways, whereas on these more traditional spectral instruments, you're getting nice, well divided curves all across the spectra.
I guess the issue there would be you're kind of blocking yourself in what's currently available in terms of fluorophores, and if new stuff comes along, so you'll have a giant filter for P on the branch and tree because P is everywhere. But if you have something that's allows you to use P with something else, like you might not be able to take advantage as well.
Indeed.
Yeah. And then, all right, so then the Sony ID7000 is the giant monster. It basically, the way they managed to get so many detectors is that they have this array that has 32 detectors. I think it's from 500 to 7-ish. And then beyond those points, they just add a bunch of PMTs. And so you'll have 32 detectors, super well characterizing everything between 500 and then below that, you have like, 3 or 4 detectors on top of it, which is, does that impact the way you would resolve these fluorophores in the low end of the emission, or so far it doesn't seem to be all that problematic?
Yeah, I'd have to look at a chart to see what the actual breakdown is. But no, we haven't had any resolution problems on the Sony. It's handled everything we've thrown at it.
Right.
Well, I would imagine that resolution would be better on the low end, right? Because isn't it the solid state detectors like the APDs are known for being better in the red, but maybe less good at the low, and so having PMTs at that low end actually kind of might boost the ability to see low numbers of photons coming in at that low wavelengths. Is that right?
That is correct.
So yeah, I think a hybrid system is probably, at least logically, seems like the way to go.
Right.
I mean, it kind of reminds me of what was said at the annual course by a Sony person, but they were talking about someone had demoed an ID7000 and they ran an Aurora optimized panel on it and it did not look good. And it's like, well, they're different instruments and you can make a panel that looks good on any cytometer, but not necessarily one that looks good on every cytometer.
Right.
So characterizing your spectral instrument and kind of knowing where it looks good and where it doesn't, you could generate good data on either one.
Yeah, we have a similar experience with trying to put our Aurora panels on the Bigfoot, and it's just not something I'd recommend. You'd really want to optimize on the actual platforms you're going to be using.
Mm-hmm.
But again, you're going from standard to branch and tree, so it's a very different optical deck. So
yeah. Another instrument that's coming up, and I haven't seen any actual formal announcements for it, but I've talked to sales reps, and Agilent seems to be coming with their own spectral flow platform. You guys have heard anything about it, or not so much?
I think I saw some marketing buzz.
Okay.
That implies one is coming, but I haven't seen any details yet.
Yeah, but this is ChUG. We get to talk about stuff even if we don't know anything about it. So
I mean, who at this point, who would not build a spectral cytometer?
Yeah.
I mean, what's the point of not having a spectral cytometer? Is there any advantage to it? to like have a, a limited number of detectors that are specifically tuned to detect an array of colors. Or I don't know. I don't know why I would ever purchase another cytometer that does not have spectral and mixing capabilities and kind of that large number of detectors.
If all you ever do is look at your transfection efficiency, you probably don't need to pay that much money.
Sure.
I think there are still labs that are running 2 to 3 colors max. They don't necessarily need it.
I guess
But no,
that's true, but
as
I
a
mean,
core
even,
facility, no, I
oh
wouldn't.
yeah, certainly, yeah. But even like, I don't know, I've run my transfected cell lines, and they just look so much nicer on the Aurora than any other instrument. Do I need that added resolution? Probably not. But if I had a, like, maybe I don't need all 5 or 7 lasers on my system, but having a 2 or 3 laser with whatever 15 detectors each laser pass, I would imagine that would be cheap enough that would make it affordable and, would make even your simple things look that much better.
Yeah, and that's an option that SciTech has with their Northern Lights, right?
Mhm.
It's spectral, but it's fewer lasers and so smaller. I don't know if any of the other ones have a
Yep.
pared down spectral offering.
The cliche question about this is spectral flow going to kill traditional flow? And Ryan seems to say yes. I say spectral will murder traditional flow with a shovel. Spectral flow is vengeful. Spectral flow I've listened to Paul Robinson's presentation where he kind of discussed the history of spectral, and he had a legal claim to technology is called a patent to spectral, and he got it really, really early, and it took forever for companies to actually to Sony to come up with an instrument. And so my take is, spectral had to wait for so long in the shadow of traditional flow that now that it's here, it's gonna, spectral flow does not forgive or forget.
It will, but it'll take time. And once
Yeah.
it becomes competitive from a pricing standpoint, which it's working on doing, as the old ones need to be replaced, I think
Right.
Spectral will get more market share.
But
Well,
to
as
Ryan's question, go ahead.
Well, I was just going to add the imaging folks would tell you
Yes.
that like spectral, I mean, that's like old technology. What have you guys been waiting for?
But I could imagine traditional flow being a technology where the only reason you would force people to specific detection wavelengths would be because you have a bunch of reagents in the background that you want to sell your users, and so the machine is just there as a way to sell antibodies but for research purposes, a core facility would never restrict itself to these type of platforms. I don't know.
Restrict itself, no, but it's nice. I mean, branching trees have their problem, but having the traditional conventional fallback in a core environment is very useful when you have those users that you just can't seem to convince to prepare proper controls
Right.
over and over and over again. You can make some wetware adjustments in traditional flow that you just can't do in spectral. You do it right or you don't do it at all.
Yeah, it's true, because when you have a branch entry instrument, the core facility buys the instrument and you decide, okay, you're going to play with these flow force for now on. Like, you don't get to play around with any weirdness. You just pick a panel that kind of works for most applications, and then people go with that.
Well, ideally, you find one with as few limitations as possible.
Right.
Yeah. Or you just buy a lot of instruments. That works too.
Yeah.
That way you have a variety to choose from.
I wanted to discuss Sony's claims as a way to revise our knowledge of flow stometry. And so if you watched any of Sony's presentations lately, there's been a bunch, and there's a couple of things that are makes your eyebrow gonna go up. And I think it's unclear to me if we're just like set in our ways and we just don't want to hear different things, or if it's some claims that are just a bit stretched for marketing purposes. So let's start with one where maybe just a general idea. If you are trying to buy an instrument, a spectral flow instrument, and you're looking at all these platforms we just discussed, what would be the point of getting the most detectors as possible in your instrument? What benefits does that entail? Where is there a point at which, yeah, you get enough detectors, you don't need more? All these type of questions.
Well, even before Spectral, my philosophy has always been buy as much machine as you can at the outset, because it's much more expensive to field upgrade than anything else. So I mean, there's benefits to just buying the biggest machine you can. But as far as utility limitations, take a look at the Sony. They have the 808 laser with the whopping 2 detectors off of it, and I don't think anybody's buying that particular laser and array because it doesn't provide any practical utility. Do I see benefits to, is there a good argument to the more is better? Well, I mean, we've already seen that anything I can run on my Aurora, I can run on my Sony, but that doesn't necessarily go the other way around. However, there's practicality. How often am I running those very large experiments? Do I need 3 Aurora or 3 Sonys, or am I good with my 2 Auroras and my 1 Sony? For a fleet, I think you build, with the workhorses, and then you have a few, high-end, really high-end machines, rather than spending, all your money on the super high end. So it depends on, what your lab's going to be, what you can afford. If you can only have 1 instrument, maybe you're looking more at the Sony than the Aurora. If you can afford multiple, I know Peter Cook in New York, he went opposite with me. He went several Sonys and then an Aurora. That doesn't make sense to me because, like I said, you're gonna, the majority of what you do, you can do on the Aurora, the significantly less expensive instrument. So have more of those, and Sony's to fill in the gaps.
So at what point do you recommend somebody goes to the Sony? So when you see someone come in, what are the features that say, oh no, you want to do this on the Sony? Is it a parameter number, colors, sample types?
It depends. Experiment size. The plate reader on the Sony is significantly better than the one on the Aurora. But yeah, I'm actually looking at the number of colors and how close they are to each other. The contiguous array in the ID7000 is very nice. So I'm going to look a lot at how the colors are dispersed necessarily, as opposed necessarily to a absolute number of colors. So.
Do you have people, what are people maxing out at your place?
Last I saw, we were still looking at 35 max color. But the people who are trying to run that, insist on doing it on the Bigfoot of all things. I think eventually they want to sort.
Yeah.
And it's problem. I mean, that particular experiment's quite problematic on the Bigfoot. And they don't have a lot of tissue, so we're having trouble with controls, that sort of thing.
because you mentioned that the last podcast you're mostly cancer research. So 35
Well,
colors
indeed.
on cancer is like it's a lot.
Indeed. But the Aurora and the Sony are really filling in the gap to the cytoff. Because the cytoff we can run 100 colors, but you can't yet. And if you're running 40 colors on the cytoff, you can do that. We have a couple at the university, but it's expensive. It's very, very expensive. And Spectral gets you, starts filling in that gap with a less expensive, very familiar technology. So
there's another layer of, and this is a marketing claim made by Sony that I kind of buy into, because it kind of matched what I believe, was it Alexis Gonzalez who published a paper about the Aurora, and he was comparing the number of lasers, like 3 lasers, 4 lasers, and he observed that the spreading error kind of goes down as you increase the number of detectors. Sony talks about their deep UV, which has no particular function except that it provides you data points for the rest of the 404s you're already running everywhere. And that allows you to get better.
Well, I bet it's also really good for autofluorescence.
Right.
I would love to do autofluorescence studies with having access to that laser.
Right.
So it kind of comes down to the more detectors you have, the more different any two similar spectra could look, because you have more regions to look for difference.
Yeah.
So I've always kind of wondered what's the point of diminishing returns? How small, and then you just don't have enough signal over whatever detector background noise.
But you raise a good point. It really depends on your applications. Like if you're going to do autofluorescence stuff, then yeah, you need cover as much ground as you can. And then, but if you're in the middle of phenotyping, and then, at 40, 50 markers, you kind of run out of ideas of stuff you stick on your cells, then yeah, maybe.
I mean, it comes also back to what Dave said with the Sony having more detectors per laser, so more detectors in each array. If he sees a lot of closely stacked colors, he'll put a user on the Sony instead, because you have a better chance of seeing more unique fingerprint regions.
Right.
But I've always kind of wondered, okay, so that's a lot of detectors in the Sony. If you doubled it, would it still be useful, or are we just going to start losing signal to the noise? But it's not a practical question. It's an interesting one.
I would imagine somebody has probably done that, back of the napkin calculation on that, knowing kind of the noise of standard detectors these days, and possibly even projecting out what could be done in the future with either similar detectors that are less noisy, or new detectors altogether. But that might be more science fiction than science fact at this point. I have to imagine. Go ahead, David.
I was just about to ask you, do you remember we did a webinar with Dave Novo where he explained the math behind unmixing, and we asked him, like, what's the maximum number of detectors that's going to be useful? And he was like, yeah, in a real world, like in the if there's no noise issues, whatever, like the more detectors you have, the better you are. But sure, like once you start bringing in this idea of noise and stuff like that, then it becomes.
I mean, I think it's the same thing that you see with, if you remember, like the early days of Diva Electronics, where they're talking about how many samples they're using to integrate the pulse of light, right? As those became higher resolution, you're actually, capturing the area signal more closely, because you're splitting that curve into more slices, so it's approaching that theoretical integral. I would imagine the same thing's happening here with doing a weighted least squares unmixing algorithm. The more data points you have to approximate the curve, the better the unmixing is going to be. So yeah, I mean, I would probably say there is some limit of return that you'd run into, but I wouldn't say that the Sony system has reached that limit.
Right. Was there something to the idea of the more detectors you have, the smaller the portion of visible spectrum, and at some point, each of these separate detectors might not get enough photons to get something that's. I'm not really good at in these type of fields, but like, was there something to it, or are we just
Well, if you
swimming
remember
photons on
you remember the annual course, build your own cytometer single photon detector using DAPI on like whatever bacteria or something like that. I mean, if we have access to detectors that can resolve single photons, I mean, you could theoretically say, I'm going to have one detector per nanometer of wavelengths, and start with that resolution. And maybe that's approaching the limit of possibilities, but
God, that instrument would weigh a ton. The Sony's already incredibly heavy.
Yeah. Back to the deep UV laser. You guys know anything, any fluorophores coming up on that line, or is that still kind of a pipe dream?
I think a couple of the existing ones have excitation peaks there.
Right.
Well, a
But I don't know if they're
surprising
any
number of
designed
things
for
have
it.
excitation peaks.
Right? Turns out.
Makes it really useful, but designed specifically for that. I swear I remember Tim from BD mentioning a few, but I could not for the life of me tell you what they would be.
Right.
I'd have to ask Kelly. Kelly would know.
Yeah, Kelly will know that. I remember a Glyphka presentation where Bill Telford was talking about the deep UV lasers, and somebody in the audience mentioned that the chemistry at that level of deep excitation, deep UV excitation, is kind of weird and might actually mess up your molecule itself and kind of makes it kind of gooey, or I don't know. That's Glyphka. What happens in Glyphka stays in Glyphka. All right. Second point that raise eyebrows, and this is something that Chris Hall brought up on the Purdue list, is this idea that you can change the voltage on your detectors to improve the resolution, and the unmixing algorithm kind of recalculates itself, so you don't have to run your controls again with the whole set of new voltages, and you still get easy access to better resolution, and basically just like messing around with your data as you acquire it. My suspicion when I hear these things is that they tried it and it kind of works in their lab, and then you try that in your lab and your face plant, you just like wouldn't work at all. Dave, have you tried that so at this point, or is that something you'd recommend?
We actually have caught a few users doing it. Because Sony told them they could, because we have the Sony guy come in once a month. He's here once a month and working with users. And we walked in on a couple of users using the instrument, and sure enough, they were doing that. And we're like, what are you doing? And it is working for them.
It hurts a little, doesn't it?
It doesn't feel right.
No.
But I personally have not done it, but my users have done it, and they've done it successfully. So good algorithm.
Can we dig a little be like on what's happening here? Because like the general notion has always been, okay, so as you increase your voltage, you get at some point where you get good separation between your markers. At that point, if you increase some more, the two don't move away, like your autofluorescence, your actual signals don't move away from one another. They just climb up the axis, your negatives start spreading out, and so you increase noise. And so there's no point in increasing beyond that point. So why is that different with the Sony platform? It's just the math behind the unmixing, or what's going on?
No, it's just, maybe you didn't optimize your controls as well as you should have. So when you get to your actual samples, and you're like, the separation is not, all that it should be, maybe maybe you can re-optimize there without redoing everything. So
I think one of the other things going on, a couple of other things. One is using PMTs instead of APDs, and PMTs in their good range are pretty linear.
Mhm.
And then the other thing that it does is it locks together each detector array. So you can't just like take UV1 up and UV3 down because that's going to shift the spectrum. So it's everybody up at some strangely optimized thing that I don't totally understand. So it's pretty good at preserving the pattern when you do that. Kind of like on the Aurora, they tell you just don't change these detectors individually, use the whole array up, down by percentage
Right.
to preserve that overall picture. And then again, the quality of your control. If you put a bad control in, it's still going to unmix very poorly.
So this is where that's the point we're arguing, Rachel and I, at the
Yeah.
Sony booth, but it has to do, and you mentioned the linearity of your detectors. And this is where I think there's a confusion, or at least in my mind, and what else is new, but there's a linear, we talk about linearity in different ways, I believe, where we talk about your typical QC stuff, like something that's twice as high on your axis is probably twice as bright. But I think what we're discussing here is the linearity between different voltage or gain values. So the APD, that Coulter made a similar claim with the Cytoflex, where they said, okay, that
Yeah, they did.
the APD is so linear, so brand linear that like you can actually change your gains and recalculate your comp matrix because it's so easy. I didn't realize PMTs were kind of similar in that specific range that Rachel mentioned, but like apparently that's the case here. But is that different linearity, or are we using the same word for different realities here, or is it all like Rachel points at the meeting was like essentially it's all grouped up in the same bag here. It's all the same.
Signal out is proportional to signal in is your linear range. Once that stops being true, you're no longer working under some linear range.
Right.
And you can look at that on pretty much anything. We use 8 peak beads and we track the ratios of peak 2 and 3 and 7 and 8. And we look for when that's no longer true.
Right.
So I don't know if an instrument is in a range and those detectors are actually generating proportional data across there.
But
then
the
it
the
kinda
thing
is.
that trips me up is I get all of that and agree and would believe the claims that are being made. But I still don't know why, as David initially described, why increasing the voltage to the detectors or gain or whatever it is would actually improve, say, a stain index measurement on a given floor once you are in that linear range. I would imagine, like on any other conventional cytometer, you do a voltration and the stain index plateaus and doesn't get any better as you increase, that voltage. But I've seen data from Sony that shows an increase in stain index on some subset of colors by just simply moving that voltage up higher on the scale or moving that data higher on the scale when they're already in the linear range.
But
So
were
why are you
they,
getting well, I mean, I
because
think
they were under optimal sensitivity, right? So you can look
what
at when you
what
maximize your separation index, but that linear range, they're slightly different. They're like slightly uncoupled. I don't know, Dave, you might be able to. This is where I start getting lost in physics and electronics.
Yeah, I don't know that I'm going to do any justice to the explanation, but yeah, there are multiple aspects to an optimized signal. It's not just that you have a maximum height or that you have a specific separation between the two. And where the Sony comes in useful is when you have set up the instrument one way, but not necessarily optimize the difference, between a negative and a positive control. It lets you sneak in and tweak that out a little bit more, but there's no magic going on just because we're using these multi-detector arrays. It's exactly the same sort of voltrations. The photons behave exactly the same way. It's just now we have software that can in process deal with changes, do recalculations on the fly, which we've not had before. Before we've had to say, okay, I didn't optimize this properly. I want to clean this up a bit more. So we have to go back to step one and rerun everything. Well, now turns out we don't. And, I still say that with hesitancy in my voice. Yes, I've seen it, but I'm old. So yes, I see it works, but I don't necessarily want to trust that. I believe in, optimize everything properly the first time. So
yeah, it brings a lot of guesswork in the game. That's like, but okay, so I just thought of this and let's see if that sticks. But I'm thinking of the starting voltage on the Sony platforms. And I'm assuming it's based on voltration. They just find like the best, like using their beads, the best separation with the lowest, and a bit like we do typically. And compare that to the Aurora array settings, which as I understand, somebody over there spent a whole lot of time running a whole lot of floor force and figured out what set of values for the gains would provide the best amount of separation overall with the set of floor force they had at the time. I'm not sure if I'm characterizing the work that's been done all that well, but say that's our starting point. Maybe playing with the voltage on the Sony platform then allows you to do these kinds of changes where, bringing this detector up, this one down, allows you better separation overall. Is that something, or am I making this up?
No, that more or less makes sense. And while this is all very interesting, the question becomes, how often realistically do you have to do that? Do you have to break down and start changing things on the fly? And, I haven't had to do it at all. My team hasn't had to do it at all. It's like fallback. It's like conventional mode on branch and tree. It's great to have. It can save your day. If you have 48 fluorochromes in and don't want to rerun thing, it's nice to have an algorithm that's smart enough to work with you a little bit to help work things out. But chances are, the instruments are designed to be user friendly, and the starting points are pretty good.
Yeah, I think that's the one thing that kind of got, and Chris Hall made this point in the Purdue list, but it kind of flips the way you work around, where you would basically set your voltage on whatever, and then you look at your data, and then you start playing with the where typically you have your voltage or gain set at the beginning of your experiment. You run your sample, everything looks fine, and you have no real reason to like switch around and try to get better resolution.
Well, I've even heard it explained that like that should absolutely be part of your workflow, putting your fully stained sample on and maximizing the signals across the lasers, by increasing the gains until you're, kind of at that high end. If you have like, for whatever reason, all your whatever UV signals are on the lower end, then you should probably be boosting up the voltage on that UV block of detectors to maximize resolution, which is, I don't know. Yeah, it definitely bucks convention, but I'm all for it if it works.
It's very similar to what we do on the image stream. when you think about it.
Yeah.
Except the image stream would do that just because it's so long to take to acquire data. So you want to be sure everything looks fine before you run into an issue. But so is there a reason other companies can't make that claim if it's just a matter of detector linearity and whatnot? Is it in other words, is it part of the software that claim is based on the way the software is built, and the other platforms do not have this feature?
It's absolutely based on the way the software is built. It has nothing to do with the hardware.
Right.
But it requires, a certain level of QC on the hardware and performance to be able to execute that.
So why is it working for Sony and not necessarily as well on the Cytoflex, which makes the same kind of claim?
Right.
Software, I guess.
Yeah.
Is it all software? Is it APDs versus PMTs and their response curves? I still don't 100% understand how these APDs are working because there are multiple things that get optimized in the background.
Yeah. Yeah, there's a lot of work behind the word gain, this stuff that's like, somebody described it, gain, as the calculated voltage. So the calculated is kind of doing a lot of work in terms of anything else to say about this point? Are we scraping the bottom here? The last idea that I wanted to bring up to your attention is whenever we talk about the way we build controls, we always say, compare the same stuff, make sure you have a positive and negative. And then the last rule is your brightest signal should be your positive control. And BD is like, Sony is basically saying, So I'm not sure. And this is something that was said in some of the online presentation I've saw. I guess their point is like, as long as you're roughly in the same intensity, your controls and your samples, you're going to be, all things being considered, there's variation across the board due to various things, and then you're going to be right about there. So I guess the rule should be amended to say, your positive control should not be super dim, because that's where you run into issues. But otherwise, is that the?
I mean, in theory, in Spectral, it should all be about curve shape, and as long as you've got, at least some reasonable signal level, you should maintain the same curve shape across the board. But I'm not telling any of my users, hey, go ahead and use, whatever the greens you want, grab the green one, because there's absolutely nothing wrong with using the brightest green for your control. But you may run into situations where that particular mid-level green doesn't cut the mustard. So,
right.
And since I can't say on all of my Spectral machines, hey, go ahead and use, a mid-level for a control, I'm not going to give them different approaches to controls. I'm going to have them, try and prepare the experiments in the same way across the board. So
yeah, I would also still try to get people to bring the brightest controls they could, because what about that small peak in that fingerprint and you bring a dim control and now it's not there, but it shows up in your sample, and now there's a little peak that isn't accounted for by any control, and the algorithm's going to have to assign those photons to something.
Yeah.
And your Spectral machine just died, but hey, we can, you can go and run it on that Cytoflex of yours in a traditional sense, if they prepared the proper controls.
Right.
Or on the S6, if you're ever willing to throw the Spectral switch,
So I feel like one of these days I will. I'm just not there yet.
So I brought up that same thing, Rachel, with kind of the disappearing portion of the curve with a low signal. And the explanation I got was basically essentially it's because it's such a small peak that it is heavily weighted against in the shape of the curve, and therefore it doesn't really impact things as much as you might think. Not super satisfactory, but I get it. I mean, if it's a small enough part of the peak that it has a potential of disappearing with a dim signal, then in the overall weighting of each individual spectral curve, perhaps it doesn't really make much of an impact anyway.
That's fair.
Yeah.
So yeah, I mean, I that being said, I also like to make and advise people to make right controls. Presumably, or maybe almost exclusively at this point, using what's those things called? The gels things.
The slingshot.
Slingshot. There you go. Thank you.
Oh, what do they call them? Spectracomp?
I don't know. There's so many things that start with Spectra these
I
days
know.
that, like, I can't keep the names correct in my head. But anyways, those things. And yeah, I mean, I guess I'm such a control freak about this that we generated 12-point titrations of CD4 in every color we owned on the Aurora, just to see what it looks like at the very brightest and the very dimmest, to compare all those curves. Did that across like 140 different colors that we get our hands on, which, yeah, I mean, definitely overkill. I would not recommend it, but having kind of a high and low for different colors, easy enough to do with something like the slingshot beads, but yeah.
Last point I wanted to bring, I just thought of this, but Sony seems to argue for the use of commutation beads across the board. They don't seem to think cells bring issues that beads don't have. So you come with beads, you're mixing with beads, and everything will be just fine.
If you can, do it.
Yeah.
But there are going to be times when it doesn't work, and then you have to go back and make the cell one.
Yeah.
I love using beads as much as possible because I've got a lot of folks with rare samples, and they're like, I don't want to make controls. I'm like, okay, here's what we're going to do.
There's a couple of posters at the last CYTO meeting where people have been trying different type of beads and the slingshot particles, and it seems every one of them seems to have some kind of issues.
Yeah.
Here and there. So I don't
They're
know.
all
These issues have
unique.
been well characterized, and we can avoid them going forward, but it's just.
It
seems to think
has to be
whatever.
tested on a case-by-case basis.
Right. But Sony seemed to think like whatever small variation you'll find is going to be okay. And so
The Sony software does have, and I might have a not quite correct understanding of this. So in SpectraFlow on the Aurora, afterwards, you can go and kind of put a comp matrix over top to try to correct unmixing errors. When you see unmixing errors or problems on the Sony system, I seem to remember like there is a way to try to correct them in the software, but it's not just overlaying a new comp matrix. It is more of a adjusting the full spectral matrix behind it.
Rejiggering the algorithm. Yeah.
Yeah. So I thought that was interesting.
Sony doesn't do anything small in their software. And perhaps that's why it works well. Even if you look at their auto comp removal, their auto comp removal is just as bad as the Aurora. But then they've added in a wizard which walks you through manually removing autofluorescence,
Yes.
doing exactly what you would do on the Aurora. They've just created a wizard, gone the extra step to create a wizard to do it. and it makes it a very easy process that works very well. So the Sony software just doesn't really take shortcuts anywhere.
Do you have the most recent Aurora software that has an improved autofluorescence finder?
Probably, but I have been out of the lab for the last 30 some days having my brain
Yes.
zapped on a regular basis. So
think
who
it's-
knows?
Yes.
It's version 6.3, if I'm correct, that's not at the time of recording, because like people are going to watch this in 10 years and be like, oh, at the time of recording, has not been released. I think it's out in December.
I have a SpectraFlow that has the Cytex autofluorescence finder in it.
Okay, so is this the tool where you get to gate
so
around
you
a
can-
subset of cells, get the signature, and feed that to the software without having to export the FCS?
Yes.
Yeah,
So
okay.
basically you can right click on your unstain and open up the, I don't remember if they call it Finder or Explorer or what,
Explorer, I think.
and you can gate on multiple populations and it will create overlaid specters and you can look at, and it'll give you similarity index and all of that. So I have found, I found that at the annual course this year and I was like, that's cool. I need that software version. So that I think is helping them as well with dealing with autofluorescence on an Aurora. But I also like Sony's implementation of finding autofluorescence is also very nice and helpful, because doing it one at a time and having to export and overlay was just mind melting.
So wrapping up, would we say something like about the Sony claims that it's not particularly wrong and probably their software is helping quite a bit in making these claims true, but overall nothing about our baggage of knowledge of flow cytometrist is there to be thrown away. We're still okay. We can continue with our work without having to question our usefulness or whatever. You know what I'm trying to say.
The Sony algorithm isn't going to replace us yet.
No, yeah, okay.
The software is your friend. It's there to work with you. Unlike a lot of other pieces of software which are there to be pushed by you, sometimes kicking and screaming to where they need to go. The Sony software, it feels like it was written by people who do Spectral software on a regular basis, that there's some familiarity with the technology. I would make the same argument about the Aurora software, that its workflow is well thought out. Not everything works as well, but it's a solid piece of software. Then there are other instruments where the software's just kind of frustrating over and over again. So
yeah. All right. Thank you so much for coming. I really appreciate your time. Thanks for our listeners for sticking with us. Leave comments. I should really start saying this stuff at the very beginning of the recording, because I'm pretty sure at this point people have figured out, oh, we're getting done there. They press stop, and then especially if like the part of the presentation where I go, okay, you need to press like and subscribe and stuff like that, and it doesn't really do much for us anyway. So
You can record that now and then edit it into the beginning. Just chop it.
Yeah. But I'm not going to do that. I'm a very, very lazy person.
You're a busy person, not a lazy person.
Bit of both.
Same.
Thanks so much. And I'll talk to you guys later.
all
Thank
right.
you.
Thanks.
Farewell.